In this video, we will learn about the Diels-Alder reaction and take a fairly deep dive into all of the various quirks and tendencies of the reaction. So the Diels-Alder reaction is a 4+2 cycloaddition, and it's extraordinarily important because it's useful for building six-membered rings. And in addition to just building six-membered rings, it's building specifically cyclohexene rings, which means that you have additional places to do other types of chemistry. And in forming this six-membered ring, you create 4 new sites that could potentially be stereocenters. And so there's a ton of complexity that's built into this single and seemingly simple reaction. So in a Diels-Alder reaction, we have what's called a diene. So that's this molecule right here, the one with 2 alkenes in it. The diene will react with a dienophile. So the reacting partner is the molecule that likes the dienophile. So we have diene, dienophile in this cycloaddition. In general, for the normal Diels-Alder reaction, we'll treat the diene as being kind of the nucleophile and the dienophile as being the electrophile. And that kind of makes sense in this example here because we have the electron withdrawing group attached to the dienophile, or the 2-atom component in the cycloaddition. On the right here, I have a second example. So this is a self-Diels-Alder reaction in which 2 molecules of cyclopentadiene are coming together to make this Diels-Alder adduct. So now let's go through some of the various features of this reaction. The first and important consideration is that the Diels-Alder reaction is quite reversible, and the backward process is called the retro Diels-Alder reaction. Here's that cyclopentadiene example again, except I've drawn it out now. And it turns out if you try to buy cyclopentadiene, it comes in a nice contained bottle, and what you find is that when you buy it, it comes to you at room temperature, and at room temperature you actually don't get isolated molecules of cyclopentadiene. You are actually buying this Diels-Alder adduct. So around room temperature, the Diels-Alder reaction is quite favorable. Just in case it's hard to see what's going on because we have 2 of the same molecule reacting, this is the mechanism that's taking place, and here's my 2 new bonds. And so since we're reacting 2 rings together to make another ring, it's a little bit hard sometimes to follow where that new cyclohexene is. So let me highlight that for you. That is right here. That's our new cyclohexene. And furthermore, I think it might be helpful to see that this alkene is that one right there. Anyway, back to the reversibility of this reaction. So if you're trying to use cyclopentadiene in another reaction, what you do is you buy the adduct and then you heat it up, and that causes the retro Diels-Alder reaction to become favored, and that gets you to your 2 isolated pieces there. The reason that temperature has an impact on the equilibrium constant of this reaction here goes back to our free energy equation. So delta G equals delta H minus T delta S. And the most important thing is that this term with the entropy in it is going to be more and more significant as the temperature value is larger and larger. It turns out that the sign of this reaction is going to be a negative entropy as written because we're going from 2 separate molecules to only having 1 molecule. So that means as temperature increases, this term is actually an additive term, which means that at high temperatures, delta G as written would be positive, so then we should go back to the left. Diels-Alder reactions are fairly regioselective. This comes from the fact that we're dealing with the HOMO of the diene and the LUMO of the dienophile. And so the pattern that comes out of all of this electronic matching is that we tend to see electron donating groups on the diene ending up either ortho or para to the electron withdrawing groups on the dienophile. So when I say ortho and para, it's a little bit of a misuse of terminology here because our products are not aromatic rings, they are cyclohexenes, but I'm still using the terms ortho and para because it's a convenient way to refer to the relationship between 2 groups on a 6-membered ring. So here's the first case where we have a diene that has an electron donating group at the 1 position of the diene. And it turns out if you do this reaction, there are theoretically 2 possibilities in terms of different isomers of the product. So you could either do the reaction as drawn, or you could flip this dienophile over. And so as drawn, you get to this product. And if you flip the dienophile over kind of vertically, so the ester is drawn on the bottom, then you get to this product here. And so in this reaction, that gives you the ortho relationship here, or the meta relationship. And as the general pattern is, we favor ortho. The reason for this is because if you think about where in the diene is going to be more nucleophilic, well, we know through resonance that electron donating groups should activate this position and that position. And then if you think about the dienophile, we want to think about where on that dienophile is more electrophilic. Well, we know through resonance that we should expect that position to be the most electrophilic. And so if we're doing our electronic matching, we should expect this position to attack that position, the most nucleophilic site matching with the most electrophilic site. And so then that forces the rest of the DielsAlder to happen like so. That gets us to this product. Right? So going the other way would be from here to there, and that would not be a good electronic match. This theory is confirmed by moving to a less electron donating group. So here, for example, if I have a methyl group at the one position instead of a methoxy group, that's less electron donating, and indeed the product distribution is a little bit less selective because there's less of the perfect electronic matching that you have in the first example here. The other possibility for the electron donating group is for it to be on the 2 position of the diene, so as shown here. And again, you have the 2 possibilities of reacting as drawn or reacting with the dienophile kind of flipped over, getting you to a now para product or a meta looking product. And again, this pattern persists, right? And you get the para product preferred and the meta one less preferred. So this is a good place for you to go through and just make sure that what you understand the most nucleophilic sites of the diene to be match up with what you're seeing in the product. Of course, these are never going to be so simple, so you can have 2 electron donating groups at both the 1 and the 2 position. And it turns out what we find is that the 1 position is a little bit more important than the 2 position. And so when I have a methyl group at 1 and 2 here, I find that I end up getting the ortho relationship between the group at the 1 position and the electron withdrawing group. That's preferred. All of this electronic matching is leveraging the HOMO of the nucleophile and the LUMO of the electrophile. And so far, I've always used the HOMO of the diene and LUMO of the dienophile. And that's just the more common way to do a DielsAlder. But it turns out you can do it the other way in what's called an inverse demand DielsAlder. And so what you do there is to put the electron donating group on the dienophile and the electron withdrawing group on the diene. In this case, I've actually got an electron withdrawing group kind of built into the diene itself. Regardless, the point is that we're still electronic matching. We've just flipped the roles of the 2 sides. And so here you can kind of do the same type of analysis and arrive at the same conclusions that we are matching the most partial negative side of the nucleophile with the most partial positive side of the electrophile to determine the regiochemistry of our reaction. From a more practical perspective, Lewis acid catalysis is really useful in DielsAlder reactions for improving both the rate of the reaction and the selectivity of the reaction. This makes some sense because if we're adding a Lewis acid catalyst, we're going to make this electrophile more electrophilic. That's going to raise the energy of the reactant, which will overall reduce the barrier for the reaction. That makes the reaction faster. And by enhancing the electrophilicity of this system, we really are enhancing the electrophilicity of this position, which then better suits this matching of the nucleophilic site and the electrophilic site. And so in this example here, I can run this reaction with no catalysis at all, and I get the 70 to 30 distribution of products. If I throw in some aluminum trichloride catalyst, this selectivity goes up 95 to 5. I can run this reaction at significantly lower temperature and much shorter times. So you may have noticed that I've always drawn these alkenes like this, matching the formation of the cyclohexene ring. And that should intuitively make sense because that does match the formation of the ring. But it does turn out to be important that we consider the conformational possibilities in dienes. So for a DielsAlder reaction to take place, we need our diene to be in the S-cis conformation, which is the one that I've always been drawing. S-cis refers to the fact that around this single bond, we have our alkenes cis to each other, or you can think of them as seeing syn to each other around this single bond. This conformation is going to be in equilibrium with the S-trans conformation, in which those 2 alkenes are now opposite of each other or anti to each other. In general, the S-trans conformation will be the lower energy conformation. So for all of our DielsAlder reactions, the S-trans conformation of the diene needs to get a little bit of energy input so that it can reach the S-cis conformation before doing the reaction. The reason that the S-cis conformation is high in energy is because there is steric interference between the 2 groups that are pointed inwards in the S-cis conformation. So let's say you have this diene and you do the DielsAlder reaction with, this is maleic anhydride. This is a pretty successful reaction, building a new cyclohexene in 97% yield. I'm going to take the stereoisomer of the diene there. So now I have the methyl group needing to be inwards on the S-cis conformation of the diene. And you can imagine that this should be sterically much less favorable than trying to get to this S-cis conformation. And indeed, it takes 100 degrees for 8 hours now to get only a 4% yield. Right? So that tells us it's really hard to get from this S-trans conformation to the S-cis conformation before we can even react. And so what we find is that DielsAlder reactions tend to be a little bit more successful if we don't have this S-cis problem here. And so we have less groups pointed inwards. So up until now, I have not shown you any stereochemistry in the products of a DielsAlder reaction, but it turns out that DielsAlder reactions are really great because they produce up to 4 new stereocenters, and they do so in a stereoselective way. This then becomes important because we have to be able to rationalize the stereoselectivity, and we do this by using what's called the Endo rule. So let me just look at first this example reaction. So cyclopentadiene plus this is called methyl vinyl ketone. In this reaction, we can get an endo product or an exo product where the difference is in the stereochemistry of this carbon right here. Right? So we get a flip there. Turns out you get a 90-to-10 ratio of endo to exo products. And these, in terms of the relationship to each other, are diastereomers because the rest of the molecule also has some stereocenters but does not change. Right? So this bridge here is still facing the same direction. One important thing to note here is that I'm always just going to draw one of the enantiomers of the endo product or the exo product, but this 90% really is also a racemic mixture. So we should have 50% of this endo product and 50% of the enantiomer, analogously for the exo product. The endo product turns out to be higher in energy, and that's because this group here is closer to the larger bridge. I know in the way that these bridged rings are drawn, it doesn't feel that way, but if you go build a model, you'll see that that's the case. This is sterically a little bit closer to all of this, and this side is sterically bigger. This is sterically smaller, and so the endo product is higher in energy than the exo product. And so by seeing that our endo product is produced more, we can infer that this reaction is taking place under kinetic control. In other words, the barrier to the reaction to forming the endo product is smaller than the barrier to forming the exo product. Right? So this is a classic example of a smaller barrier leading to a less stable product, preferentially. The reason that we have this lower barrier toward the endo product is because there are what are called secondary orbital interactions that stabilize the endo transition state. Let's look at that now in both drawing form and in models. So I have in drawing form the relevant molecular orbitals that are involved in the reaction. So I'm going to be reacting my dienophile with the diene at the ends, as is always the case. So that's going to be from here to here, which is corresponding to that interaction, and from here to there, corresponding to this interaction. Okay. So I'm, in my mind, always viewing the diene as above and the dienophile as below, coming together. That gives you one of the enantiomers, and if you do the opposite, where the dienophile is above and the diene is below, that gives you the other enantiomer. In the product, these red and purple connections are becoming the new sigma bonds. So in the endo product, this is the purple connection, and this is the red one there. And so the big thing that we get is that if you kind of imagine that the carbonyl here is further back in my drawing, so a little bit away from us, compared to this alkene here, then you're actually nicely lined up to have an additional interaction that's not forming a bond, but is still an interaction. Because this phasing here of this carbon is nicely lined up with the phasing of the carbon there. So that's from this carbon to that one. And so that secondary orbital interaction is what's stabilizing the transition state here. Let me pull up a model of what this whole process looks like. You can see by looking at this that our reaction is not happening side to side like it does in our drawings, like the way that I have it drawn up here, but rather it's happening with those pi bonds interacting, so kind of a face-to-face, I guess, drawn this way. I've tried to orient this model the same as I have it in my drawing here. So if we're looking for that secondary orbital interaction, that's going to be between these two carbon atoms. So on the bottom, that's the carbon of the carbonyl, and on the top, it's one of the carbons in the cyclopentadiene. It will help for me if I kind of take you through this. So again, here's that side-by-side view of the process. And now from above, you can kind of see how the yellow atoms are where that secondary interaction is, and they're nicely overlapped with each other. The bond forming is not happening at that yellow atom. It's instead happening out here at the purple side and down here at the red side. Let me just contrast that with the exo reaction in drawing form first. So again, we are setting up a reaction kind of the same way. I'm thinking the cyclopentadiene above, the dienophile below. Again, I'm going to have my bond forming locations being like so and like so. So from red to red and purple to purple, corresponding to this interaction and this interaction. In my drawing, I unfortunately drew the enantiomer, so that corresponds to that and that bond. Now, if you look at this, because of the way this carbonyl is exo to the transition state, what we have is now that there is no secondary orbital interaction. That then causes us to have a higher energy transition state. So let me again pull up a model that kind of is matching our drawing. So now you're looking at the exo reaction of these two reactants. Again, I'm showing to you as the drawing was done, but you can kind of see that we have the same thing. So we're reacting face to face, and if you want to look at it from this angle, it looks kind of like that. And in the reaction, we're going to be reacting from red to red and purple to purple, but if I highlight that same carbonyl carbon, you'll see that it is not lined up to have any secondary orbital interactions with any other atom, right? And so because of that, the exo transition state is higher in energy. Another thing that people observe here is that the exo transition state appears to take up more volume because you have groups pointed out in both directions, compared to the endo transition state, where everything's going to compact it together into a smaller volume. So let's look at some animations of these reactions taking place. Let's look at the endo reaction first. So we're going to look at this from above right now, and if we go through the animation, you'll see how that endo secondary orbital interaction is kind of maintained. It's hard for us to see exactly where that cyclohexene is being formed from this point of view. So let me turn this structure a little bit. And there you can kind of see the cyclohexene that's formed and how the carbonyl or the ketone is pointed kind of downwards in the structure. I'm going to run through this animation again, but going through the animation from this perspective. So if we do that, what we'll start off with is these two molecules face to face, and then they come together, form that cyclohexene ring, and that gets us to our product like so. Now let's look at the exo transition state. So what you'll see is that, again, the cyclopentadiene is above, those molecules react together, and at no point in time is that highlighted carbonyl carbon ever close enough to any other pi bond for there to be an interaction. As per the other animation, it's hard to see that cyclohexene, so if I turn it this way, you can see the cyclohexene ring being formed, and we can go through our animation again this way. And watch that process. So here the molecules are coming together. There's our new ring formation, right, getting us to this product, which unfortunately, as I've drawn it, is the enantiomer of what I drew up here. So hopefully that was helpful in terms of visualizing the process of the endo reaction. But of course, if given a reaction and predicting stereochemistry, this computational modeling or trying to draw the orbitals out on paper will not be very useful for doing this quickly. So there's actually some patterns that we can extrapolate from this whole process. So if we take any generic Diels-Alder reaction, where I'm now labeling some groups on the diene and the dienophile, we can clump these groups together. So the groups on the outside of the diene here, so I think of them as pointed up and down, are going to always have the same direction in the product. They're always going to be syn to each other. The groups on the inside of the diene are always going to be syn to each other in the product, and analogously for the groups on one side of this dienophile and on the other side of the dienophile. So in the endo reaction, where I'm placing the groups C and D endo, then my transition state looks like this. My reaction is going like so. And that's going to get me to this product. And it might be hard to see, but it's worth building the model of this. So building the model of the diene and the dienophile and just convincing yourself, if you sandwich them on top of each other, that the groups C and D are going to end up facing the same direction as the groups X and W here. And so they're all going to be syn to each other. So again, these groups and these groups all syn to each other. And so then conversely, the groups that are inside here, YZ, and the exo groups are going to all be syn to each other. So let me just show you this for when CD is exo. So same idea, I have my reaction taking place. Now I have the C and the D group exo, like that. And that gets me to the product here, where now, if we look at the W, X, C, and D groups, we should be able to see that W and X they're always permanently syn to each other, but WC, WD are going to be anti to each other, and XC and XD are also anti to each other. So I know looking at that seems like way too many things going on, but really it probably is easiest to just distill this all down into a simple rule here, which is what I use. The endo groups on my dienophile, so C and D, are always going to be syn to the outside groups on the diene, in this case W and X. From that, you should be able to extrapolate every other relationship, because you know that group C is always anti to group A, or I guess if this is wedged, that's going to be hashed, and you know that group Y is always going to be the opposite of whatever W is. So let's try to put that into action here. So for this DielsAlder reaction, the two things I need to do are first do the reaction to figure out what the cyclohexene product looks like, and then fill in my stereochemistry. So the reaction itself should be hopefully not too bad. That's forming a new 6-membered ring. That's going to have a cyclohexene in it, so you can always just draw that. And if you kind of figure out where your diene piece is, that's this piece right there, then that helps you fill in what else is attached. So it looks like my cyclopentadiene ring has to be attached at the ends of those highlighted carbons. So I'm going to fill that bridge in right there. And that tells me that the outside 2 carbons here are coming from those 2 carbons in my dienophile. So then if I go ahead and draw in all of that, I should have that, and ester top and bottom. Okay. Then I go through and evaluate the endo and exo characteristics of my reaction. So let me duplicate my drawing here. And to fill in the stereochemistry, now I'm going to notice that the groups right here are going to be endo. Right? That's going to have the carbon that can do a secondary orbital interaction with the diene. So that's going to be endo. And the groups that are outside of my diene are just hydrogens. So that's those 2 groups right there. Because of that, then, I should be putting the endo group syn to this outside group. So that means that this hydrogen and these esters should all be either hashed or all wedged. So let me just go ahead and do that. So I'm going to do that, and then I'm going to change this piece out here. Finally, this hydrogen down here, and then that's the stereochemistry of our product. You could also draw this differently, so you could also draw the bridge as wedged and not draw the hydrogens, right? That's going to show the exact same thing. Another example, so now I have a different isomer of the dienophile. Same thing, I'm going to go through, draw my product here. Again, I have a cyclohexene. I know that I have this bridge because I just did that example above. And now I have still 2 esters attached out here. Where again, it's kind of the same pattern of that was my diene, and this is my dienophile showing up. But the stereochemistry is going to be different now, because if I go through and think about what's going on, now my outside groups are still hydrogens. So that, let's say those are still going to be out here. Let's just put them arbitrarily syn to each other. But only one of those esters is ever going to be endo. So what that means is that I can only have one of these esters being shown as being syn to those hydrogens, and the other is naturally forced to be anti to those hydrogens. This should make sense because in the dienophile, the esters are anti or trans to each other. So in the product, they need to be anti or trans to each other. One last example here. So in this reaction, should be able to predict the product fairly quickly. So I'm going to have my cyclohexene ring that's coming from this diene piece right there and this dienophile piece right there. I'm going to have my methyl groups coming up and down from the ends of what was my diene, and I'm going to have another ring sticking out of the other side. So then here I should expect my outside methyl groups to be syn to the carbonyl and syn to this CHOH here. In rings, usually we don't draw the ring bond here as being wedged or hashed. And so the tricky thing that you have to take care of here is to draw the hydrogens kind of opposite, right? And so what I'm really saying is that the hydrogens here are going to be anti to the outside methyl groups. So let me fill that all in here. So I have my hydrogens anti to the methyl groups, which are now wedges. And so that's the product we would expect to be favored by this Diels-Alder reaction. And you should also have the enantiomer of this product, where it's hashed methyl groups and wedged hydrogens. So that was a deep dive into the Diels-Alder reaction, which has this deceptively simple pericyclic mechanism, but is able to generate this wide amount of complexity when it comes to its regioselectivity and its stereoselectivity. Diels-Alder reactions are really great because they are super efficient and they generate a lot of complexity. In these reactions, there's no byproducts. You just add two molecules together and all those atoms go into your product. So that's called very atom economic. And you create these 4 potential new stereocenters. And so that allows you to really build a lot of complex 3D shapes that can interact with biomolecules in very specific ways.